right, today is Thursday, May 7th, and we're going to be working on a list of modified problems that cover a variety of topics. Primarily, we're going to be talking about bivariate data, and we'll see some hypothesis testing as well. Please don't forget this Saturday will be the last stats Saturday. Highly recommend that you get if you have an opportunity to get Stat Medics Units 6 and 7 done prior to Saturday. It'll help you out, but it's certainly not required. I think it would be to your benefit to be there. Okay, so first problem. First off, this first problem, when I initially submitted it, I didn't realize it had a natural log in it, which made it inappropriate for this year. So I went and readjusted it, although keeping true to mainly what it said. Huge long problem. This is a question 6, or was based on a question 6 problem, which means it's an investigative task. And even though we have some longer problems this year, we will not have investigative tasks. You don't need to worry about that. So, which is why I certainly wouldn't worry about there being any natural logs this year. Scientists interested in preserving natural habitats and minimizing the possible extinction of certain bird species conducted a study to determine if it's better for conservation groups to purchase a few large nature preserves or many small preserves in order to meet these goals. Basically, you have birds dying, and they're trying to determine whether or not they should purchase these large areas or small areas. The scientists studied 13 randomly selected islands. That's good because they're random. That means hopefully they're going to be representative of other islands of different sizes to determine the risk of extinction for bird species. Islands are thought to be a good imitation of what would happen in a nature preserve because of their isolation. If a species lived on only one island, it was considered to be at risk. Scientists have determined that whether or not one species becomes extinct is independent of whether or not another species becomes extinct. So extinction is independent. I seriously doubt it. In 1990s, scientists counted the number of at-risk species on each of the selected islands. They returned to these islands in the year 2000 to see whether the species still existed on the islands. Species that were present in 1999 but absent in 2000 were considered extinct. Well, that seems obvious. Data collected by the scientists are given in the table below. So we have this table, and I'm just briefly talk about it. Number 113 is through 13 is just the random, it is the numbers that they assign to the islands, and they assign them based on size. So island 1 had 46 square kilometers, and island 5, 26, and then we got all the way down to island 11 through 13 all had 1. We have a list of species at risk for 1990, and then how many of them had died off by the year 2000. The proportion extinct, although this is might be maybe a little bit obvious, I'm still going to show you. That the way they got that is they just put 8 over 75 for the first one, 3 over 67 for the next, 8 over 67, etc. And that's how they got that final column. Okay, so one scientist involved in the study believes that large islands, those with greater than 25 square kilometers, and if we look at that real quickly, looking at it greater than 25, that's this group right here. Greater than 25. Are more effective than small islands, those with areas of less than 25 square kilometers, protecting at-risk species. The scientists noticed that for the study, a total of 32 of 287 species of the large islands became extinct. So on the large islands, we lost 32 species out of a total of 287. On the small islands, they lost 53 out of 220. Assume the probability of extinction is the same for all at-risk species on the large islands and the same for all risk species on small islands. Do these data support the scientists' belief? Give appropriate statistical justification for your answer. So they didn't say confidence intervals, so I don't think I'm supposed to be running a confidence interval. And he also says he believes that the large islands are more effective. Well, if they're more effective, that means they should have fewer dying off. So proportion 1 is proportion 2, and I defined that proportion 1 is the large island. And proportion 2 is the small island. And we would say, hey, if it's more effective, we expect to have fewer birds or fewer things going extinct on the large islands. So proportion 1 should be less than proportion 2. And that would be our proportions for the hypothesis test. The conditions on this are not nearly as clear as they should be, and not nearly as clear as I expect them to be on the exam. First off, we have a random sample of 13 islands, and that was given, and it's thought to be representative of both large and small islands. To me, that's a fairly small sample, but nonetheless reasonable. Independence, extinction of one species is independent of that of another. I should have just said that that was given because they told us that. Otherwise, I wouldn't know it. Then I need to sit there and go check to see whether or not the sample sizes are large enough. I had 32 going extinct on the large island, which is bigger than 10. I had 255 that did not go extinct, which is also greater than 10. On the small islands, 53, which is greater than 10, went extinct. And so basically we sit there and we see, all right, we have enough to say that they're going extinct. One thing that I thought was odd about this, or I think is a little bit disconcerting, is we didn't do the n is less than 10%. Well, keeping in mind, n is less than 10% is for an independent statement, and we do have an independent statement. So that's good enough in this situation, and technically they told us they were independent, all right? So we weren't worried about the fact that we were actually sampling the entire population. All right, so those samples are large enough to use the normal approximation. And I went ahead and defined P1, which was 32 birds out of 287 on the Big Island went extinct, or about 11%, and then 53 out of 220 on the Small Island for about 24%. And right away, we look at those proportions and go, you know what? There appears to be a difference, but we need to make it statistical evidence. We can't just work on the proportions. So because it's a hypothesis test, and in a hypothesis test, my null hypothesis is that they're equal. We have to assume that they're equal until we prove otherwise. So consequently, a better estimate, if they are equal, is to combine both samples together, to combine the large island and the small island to make a single sample. And that gives us our combined or our pooled. When I combine those values, 32 from the large, 53 from the small, 287 total species from the large, and 220 on the small, I end up with 0.1677. And that would be, if they were equal, which is our assumption, that would be my best estimate to the proportion. So I go ahead and set up my hypothesis statement. Write down my formula. I plug in, and there's my proportion from the Big Island minus the proportion for the Small Island. And then this is my pooled value, or my combined value, over the proportion, over the sample size from the large island. Then we also have the same pooled value over the sample size from the small island. And so then we need to go ahead and run our test. Well, because it's a two sample, this is just going to be a two sample proportion. So it's FATS test, two proportion Z test, 32 extinct on the Big Island out of 287, 53 extinct on the Small Island out of 220. Make sure that I have the less than inequality, because that's what I had in my HA, my alternative. And I calculate, and I find out that we expect 3.86, or about 3.86 standard, or 83 standard deviations away from the mean, and that is a long way. And the probability rounds to, and if you just put approximately 0, that would have been fine, but approximately 0, 0.0006 or 0.0005 if you truncated, all of those would be acceptable responses. So our p-value is approximately 0. We reject the null. There's sufficient evidence that alpha equal 0.05 to suggest that the true population proportion of bird species that go extinct is less on big islands than it is on small islands. So the data then I need to answer the question, and the question was, does the data support the scientist's belief? The data support the scientist's belief that big islands protect bird species better than small islands. And all right, another scientist. Oh, thankful for the other scientist. So we get to do more work. Who worked on the studies thinks that the proportion of species that became extinct is more directly related to the size of the islands than simply to whether the islands are as groups are large or small. The scientists investigated the relationship between the proportion of extinct birds and the area in square kilometers of islands. A least square analysis was conducted on the proportion of extinct, and the regression analysis output, the scatter plot, and residual plots are shown below. So let's real quickly review a couple things, because even though regression isn't specifically on the test, what's not on what they really mean by that is you don't need to do a hypothesis test and you don't need to do a confidence interval for regression. But everything that I'm going to show you here is possible to be on the test. So first off, these sum up to 11, which tells me that my, well, actually this should have been on 11 right here. That should have been an 11. But anyway, my 13 should have been my sample size. Right here, we have the standard deviation of the residuals. Right here, we have the R square. R square adjusted is just there to confuse you, not necessary. This right here, the one would be my slope. And this right here, the one above it is my y-intercept. This is my slope. Okay, that's going to be important to know where that is. And I think that'll be the most things that they would care about. And so let's look at this. All right, so first off, when I look at this, I go, you know what? I can definitely sit there and go, you know, this is reasonably linear. I mean, it's obviously, so if I was drawing a line of best fit, it might look something like that. You're like, yeah, there's definitely a downward pattern, and I feel kind of good that a line looks pretty good there. Then I look at the residual plot, and although I have a bunch here, it's just because I have a larger sample of small islands than I do of large islands. Everything is randomly spaced. Big islands are below, small islands are below, small islands are above, big islands are above. So the residuals are fairly random. So I really am not too concerned about I'm really not too concerned about the randomness aspect. So it looks like a regression model would be appropriate. Is a linear equation an appropriate model to justify your answer? A linear model is appropriate because the random sample, that was important to say, resulted in a reasonably linear scatter plot and a random residual plot with no obvious pattern. Okay, so that's, you need to have both of those statements, but I will tell you this, the most important part is the random residual. It's nice that the scatter plot is linear, but you must have a random residual plot. All right, provide the equation of the least squares regression model. Well, y hat equals 0.263388 minus 0.004165x, and I just got that from up here. I pulled that from up here. There's my y-intercept, there's my slope. But if I do it like this, and there's nothing wrong with doing it like this, then I have to define my y hat and I have to define my x. However, if I build it into it, I can just put the hat sign over the proportion of extinct birds, equals 0.266388 minus my slope times the area of the island. If you write it like this, you do not have to explain it. If it makes you feel more comfortable, do what I did and write both. But that way you don't have to define your variables. And they like that. All right. Define the slope and y-intercept in context. Well, we already said the slope is 0.004165. So remember from Algebra 1, change in y over change in x. So basically that over 1, and it's fine to write it as a decimal. Please note that our proportion of species extinction over 1 square kilometer. And what that means is for every 1 square kilometer increase in the proportion in area, the proportion of bird species going extinct decreases by this amount. So as we increase the island size, the amount of extinction diminishes. So increasing island size seems to decrease extinction. Vice versa, decreasing island size increases extinction. I just needed to choose one way or the other. The y-intercept. Well, again, we just read that from the computer printout. If the island had 0 area, which makes no sense, but if there is 0 area, we'd expect that 26.6% of the birds living there would go extinct. I'm thinking they would all go extinct if there was no island, but that's just me. But that's what it means. Calculate and define the correlation coefficient. Well, they didn't give me the correlation coefficient, but they did give me an R square of 71.9. So I take the square root of that. I take the square root of the 0.719, and I use the sign of my slope. My slope was negative, so consequently my correlation is negative. Slope is negative, so consequently my correlation is negative. So in this case, there is a strong negative linear correlation between the area of the island and the proportion of bird species going extinct. So there's a strong negative linear correlation between the area of the island and the proportion of birds species going extinct. All right. I went ahead and put this on the next page just to make it easier for me. Calculate and define the coefficient of determination. Well, coefficient of determination, again, is just R squared right here. R squared adjusted is just there to mess with your heads. We don't need it. So the coefficient of determination is this. So 71.9% of the variation in the proportion of bird species going extinct can be explained by the area of the island. And all that means is the amount of variation, how much the extinction rate changes or extinction proportion changes can be explained by area of the island. Define the standard error. All right. Well, standard error is standard error of the slope. It's most often marked as standard deviation. That's that value right there. And basically identify what it is, because the slope is estimated from a sample. Other samples are likely to differ and provide different slopes. The standard error of the slope lets us know how much variation in slope we could expect from different samples. All right, just a long sentence from your card. I hope they don't have you write that, but nonetheless, it's on your card. Fairly easy. Define S in the context of the problem. Well, first off, S again was found in the corner. And it's the standard deviation of the residuals, which tells us how much we might expect the proportion of actual bird species to vary from amount predicted by our equation. Or it's how much we expect it to vary for a given amount of area. All right, something along those lines. The proportion of bird species extinction to vary from the amount predicted or the amount for a given quantity of island area. Calculate the residual for an island 36 kilometers and for an island of 3 kilometers. Well, the very first thing I need to do is write down my equation, and then I'm going to plug in 36, and I'm going to plug in 3. All right, when I do that, I end up getting a proportion for 36. This is what I expect to happen. That's what I predict to happen. And this is what I predict to happen when I plug in for 3. When I look back at my table and I look at 36, what I actually observed was 4%. Now, what I predicted was 0.04. I mean, excuse me, what I predicted was 0.1164. What actually happened was 0.04, and a residual equals the observed minus expected. So observed, what actually happened, minus what I predicted would happen, and that gives me that. So this is my final answer for the 36. On the 3 kilometers, I predicted 25%. And on the island with 3 kilometers, it gave me a proportion of 25%. So in this case, my residual is almost 0. This one should have been almost exactly on the line, exactly 0. Okay, so my prediction was really, really good for that one. It wasn't as good for this one. Getting towards the end on this. Would it be appropriate to use this model to predict for an island of size of 350? Justify your response. And the answer is never go beyond your data. All right. So since our data only had island sizes from 40, largest of 46 to smallest of 1, we should not go beyond that area. So it would not be reasonable for us to use for predictive purposes. Only because our sample doesn't represent islands of that size. Remember, samples are supposed to represent your population. Well, we don't represent a population that included islands of 350. We should only do it for islands of 1 through 36 inclusive. And the reason is we don't know if there's changes based on as island size increases. We have no way of predicting. Without having a sample to at least use an estimate. Finally, a conservation group with a long-term goal of preserving species believe that all at-risk species will disappear whenever land inhabited by those species is developed. So development, in this case, they believe will get rid of the endangered species or kill off the endangered species. It has an opportunity to purchase land in an area about to be developed. The group has a choice of creating one large nature preserve with an area of 45 square kilometers and containing 70 at-risk species. Okay, so 45 kilometers, 70 at-risk species, or 5 small preserves with an area of 3 kilometers each containing 16. Now that's interesting because this one, 5 times 16, they're looking at 80 endangered species, and here we're looking at 70. Which choice would you recommend and why? All right, and they want their long-term goal is to preserve species. So I'm going to assume that they want to preserve as many as possible. So I immediately look at this and go, gosh, the 5 small islands has 80. This has 70. Initially, this looks better, but we need to do a prediction as to how many are actually going to go extinct because we know the small islands tend to have a higher extinction rate. So when I plug in the size, and so basically I come up with, I predict the proportion who will go extinct to be 0.079. Well, if 0.079 is the proportion to go extinct, and I have 70 birds or 70 species, 1 minus that is the proportion who live. This is who die off. This is what live. So when I multiply that, I end up with 64.47 species saved if I go with a large island. if I go with the 45. On the other hand, when I plug in and try it for the smaller island, it has the 3 kilometers, and I go, okay, we have a 25% of the species go extinct. All right, so these are the ones who die off. 1 minus that is who live. I multiply by an 80, and I go, oh, this one saves 60. So the small one says we save 60 species, the large one saves 64. So consequently, this one saves more, so therefore it's better. Now, please remember, just doing the math doesn't answer the question. That's your justification. To save the most bird species, I would choose the large nature preserve, although the large preserve has only 70 endangered species and the 5 nature preserves would have a total of 80. We'd expect to save 64 in the large preserve as to only 60 in the small preserve. So that makes sure you always not only show your justification, but provide an explanation with your justification.